then I can finish the rest of it next time. So this picture on page 100 I thought was really cool. Kind of explains the interpretation of what these relative homology groups actually are. So here's something. It's like this whole thing is X, and this part here is A. And so if you have a one simplex, or singular one simplex, that starts and ends in A, that's considered a relative one cycle. So essentially, you can sort of think about it as they're end cycles, end chains, end boundaries, but this part is being modded. So we'll actually see explicitly towards the end of the chapter that we can prove that these relative homology groups are related to quotients of another type of homology group, which we'll find later. But this next page here, let's see. So they say, recall the definition of a quotient complex, which remember, we essentially just define term-wise. So if we're quotienting X by, if we're quotienting the singular complex of X by the singular complex of A, what we get is Sn plus 1 X over Sn plus 1A, Snx over Sna, Sn minus 1x.
You're back on 99 now, I
Sn
think.
minus 1.
Yeah.
Yeah. A.
That picture was from the future.
So then, if you remember the definition of the differentiation maps, so this is the n plus 1th one, and this is the nth one, was you define it by x on gamma coset. We just define it to be partial n gamma plus Sn minus 1A. And that was well defined for some reason I don't remember, but it's well defined. So now he says the kernel of this map is equal to the set of gamma plus Sn of A such that partial n gamma is an element of Sn minus 1A, which is what we're pushing by. So essentially, that this is 0, right? With respect to the group structure we're dealing with. And the image of the n plus 1th differentiation map is gamma plus Sn of A, such that Y is an element of the image of our old n plus 1th differentiation operator from Sn of X.
Bn of X.
Oh yeah, so that's not an element.
Sorry.
Yeah, that's equal to
About
Bn
n
of
boundaries.
X. So then we have a definition. The relative n cycles mod A, I'm just going to write it out, is equal to set vol gamma in Sn of X such that the nth differentiation operator acting on gamma is an element of the n-1 chains on A. And the group of relative n boundaries on A, which you write like this, the n of xa is equal to the set containing gamma on the Sn of x such that y minus y prime is an element of the n boundaries on x for some gamma prime and singular n chains on A. So we have theorem 5.11 is for all n greater than or equal to 0, hn of x, a is, as we would expect, isomorphic to zxa mod bn xa. So the proof here by definition we have hn of xa now is equal to the kernel of the nth map over image of the n+1 map, which is what we defined before. And they say it is easy to see from our remarks above, namely this stuff, that the kernel of the nth differentiation map is equal to Zn xa mod Sn of A. So right, if you look at this, the definition here, like I was saying, this being an element of Sn minus 1 of A, essentially, oh no wait, I'm looking at the, no sorry, essentially it being 0, so it's essentially these, but then mod Sn of A, so that's pretty easy to see. And similarly, the image of the n+1 differentiation map is equal to v sub n xa mod S sub n of A. So now, by the third isomorphism theorem for groups, which is, in our context, since everything's abelian groups, we don't need to worry about it being normal or not. So these are all groups, then this is isomorphic to G mod K. So this mod this is isomorphic to cycles mod boundaries. Therefore, hn of x a is isomorphic to bn of xa mod, oh, other way around, cycles mod boundaries. That's that. Let's see. Yeah, I guess I can just leave that next for last time. It's almost time anyway. It's 3:30.
Yeah, so it's a pretty good place to stop.
All right. Thanks, guys.
Thank you.